Hello and good morning, dear students. Today we are starting chapter number 4, which is Lagrangian and Hamiltonian formulation. So, this is a comparatively new chapter or new concepts. First of all, we are going to see introduction of this chapter. So, Lagrangian and Hamiltonian formulation, this chapter. Here we are dealing with formulations which is parallel to Newtonian mechanics. We studied Newton's laws of motion and we can use those Newton's laws of motion to find out, we can say, differential equation of motion of a object. Now similarly, differential equation of motion of a given object can also be found out by Lagrangian and Hamiltonian formulations. So how such differential equations and how these formulations work? So Lagrangian and Hamiltonian is more superior formulation than Newtonian mechanics that we are going to study in detail as you learn how to apply this Lagrangian and Hamiltonian. So with this introduction, we start first point, limitations of Newton's laws of motion. So limitations of Newtonian mechanics. So what are the limitations of Newtonian mechanics? So Newtonian mechanics is having certain limitations. So first of all, Newtonian mechanics is applicable only for inertial frame of reference. Okay, so we know that what is mean by inertial frame of reference. Inertial frame of reference in which the frame of reference which does not have any acceleration. So acceleration is zero. Okay, if acceleration of that frame of reference is non-zero, then such frame of reference is known as non-inertial frame of reference. So here, Newton's laws of motion are not applied in non-inertial frame of reference. If we apply Newton's laws of motion for non-inertial frame of reference, then certain forces which are we called as forces of that reference frame arises into picture, and those forces are not real forces, those forces are pseudo forces. Okay, so pseudo forces we have to take into account. So this is one of the limitation of Newtonian mechanics. Another limitation of Newtonian mechanics, which is limitation number 2, is Newtonian mechanics is oftenly applied for velocity which is very less than c. Okay, so here relativity came into picture. Okay, so Newtonian mechanics is not applicable for the particles which are moving with velocity of light. Okay, so such particles which is moving with velocity of light, we have to apply relativistic calculations. So Newton's laws of motion are not applied for such particles. Then next limitation of Newtonian mechanics is that if we have very large number of identical particles, so if we have very large number of identical particles, for such identical particles, if we study interaction of those identical particles, okay, among themselves, for such interactions, for such interactions, we have to use laws of statistical mechanics. Okay, then Newtonian mechanics is not applicable. Why Newtonian mechanics is not applicable? Because for such very large number of particles, Newton's laws of motion are invalid. Okay, Newton's laws of motion invalid because since the number is very large, okay, since the number is very large, all the particles, the we can say two or more particles can satisfy Newton's laws of motion, but if we have very large number of identical particles, so it is not necessary that all particles should follow these laws. Okay, so there we have to use, or we have to talk in terms of probability. That's why we have to apply statistical mechanics. So these are the three limitations of Newtonian mechanics. Now we are moving to Lagrangian and Hamiltonian formulation. For Lagrangian and Hamiltonian, there is very basic concept. What is that concept? So very basic thing we have to understand first. First one is constraints. Okay. Next one is degree of freedom. Okay. Then here constraint and its types. So types of constraints, degree of freedom, generalized coordinate, and configuration space. So first of all, we are going to study constraint, then types of constraints, then degrees of freedom, then generalized coordinate and configuration space. So we are going to study one by one. So first of all, we start with constraints. So what is mean by constraints? Constraints are known as restrictions on the motion of the system. So constraints are restrictions on motion of a system. Okay. So oftenly, what are those restrictions? Those restrictions are occurred due to constraint forces. Okay, because of constraint forces. So if we study mechanics, okay, suppose a particle which is moving in a one dimensional plane, in one dimensional line. Suppose this is a line and this bead is moving on this line. In this case, what is the restriction or constraint on this particle? We can say that particle move like this only. So this is the restriction, okay, which is applied on this bead. Now, now if particle is moving two dimensional, okay, here we have shown one dimensional, two dimensional. Suppose that particle is moving on this board here and there, then what is restriction on this particle? That it cannot leave that board. So now next, constraint forces. What are the constraint forces? Constraint force on this particle is gravitational force, okay, which is pulling down. Again, this normal reaction of this rod, okay, which is always present when that bead is on this rod. So that normal reaction, okay, of this rod is also constraint force. Similarly here, normal reaction of this table, okay, suppose this is table and it is moving on this table, so normal reaction of this table. So normal reaction is the constraint force which is responsible for the motion. Now you can take many examples and you can see what are the different type of constraints. Again, suppose if you take simple pendulum which is moving like this, so what is the constraint on this motion of that simple pendulum? This bob is moving like this, swing in this plane of a blackboard. Okay, so for that case, first of all, length is constant, and suppose this is x and y coordinate, z coordinate is 0, because this bob can move only in the plane of board. So that's why z coordinate is 0. Again, if you take rigid body, okay, so for pendulum, what are the constraint equations? Suppose m, this is L, okay, this angle is theta and bob is moving like this, suppose this is x coordinate, this is y coordinate, then z is equal to 0. Okay, so this is the constraint equation. And another constraint equation is x square plus y square is equal to L square. Okay, suppose this distance is x, this distance is y. When that bob is moved like this, then x square plus y square is equal to L square. Okay, so this is the another constraint equation which came into play. So these are the two constraint equations. Okay, now for rigid body, we know that definition of a rigid body is that a distance between 2 points on the rigid body always remains constant, whatever the force we are going to apply. So for any force, distance between 2 points is always constant. So we can say, suppose this is a rigid body, okay, and these are the two particles xi and xj, and this distance is cij. We can say xi square, okay, minus xj square is equal to cij square. Okay, so this is the constraint equation for rigid body. Now for rigid body, for pendulum, these are the two constraint equation. Now we are moving to next point, types of constraints. Now here equations that we write for showing constraint on the motion are known as constraint equations. So depending on those constraint equation, constraint types are classified. So first of all, first type is holonomic. So what is mean by holonomic constraint? So if constraints are expressed in the form of equations, so this is the constraints can be represented in the form of equations. Here you can see these are the equations. Okay, so if constraints are expressed in the form of equations, then such constraints are known as holonomic constraints. Okay, next one is non-holonomic. If constraints are represented in the form of inequalities, okay, so if constraints are expressed in the form of inequalities, then such constraints are known as non-holonomic constraints. See here examples of non-holonomic constraints. Suppose if this is the circle, okay, and particle moving in the circle, so it cannot came out of that circle, then how the constraint equations are represented? Okay, suppose the particle is over here, suppose r is the radius of circle, then we can say x square plus y square is less than equal to r square. Okay, if that is equal to r square, we can say that particle is on the surface of circle. If that is less than equal to r square, then we can say that particle is inside the circle. Okay, here. So this is the type of constraints. Or if that particle is outside the circle, then constraint equation is greater than equal to r square, with the condition that particle cannot came inside the circle. So it can came like this and go like this. Okay, so for such motion, we can say if instead of circle we have spherical shell or sphere, and if particle is outside that spherical shell which cannot came in this spherical shell, then our constraint equation is x square plus y square plus z square is greater than equal to r square. If that particle is moving inside surface of spherical shell, then our equation is this is less than equal to r square, where r is the radius of that spherical shell. So such here we have inequalities. Okay, whenever we does not have equations, we have inequalities, then such constraint are non-holonomic constraint. Time part is also important in holonomic and non-holonomic constraint. If in holonomic constraint, in the form of equation as well as time is also present. Okay, so if the equation contains time, then such constraints are also holonomic constraints. Now, next type of constraint is rehonomous and scleronomous. So, what is meant by rehonomous constraint? If constraints are expressed or constraints are time dependent equations. Okay, if constraints can be expressed as equations which are time dependent, then such constraints are rehonomous. And if constraints are time independent, okay, then such constraints are scleronomous constraint. If constraint can be represented by time independent equation, then such constraints are scleronomous. If constraint equation are time dependent equations, then such constraints are rehonomous constraints. Okay, now with this, types of constraints are finished. So you all know what are the constraints, what are the different types of constraints. Now we are moving to next point, which is generalized coordinates. So before generalized coordinate, we must have degree of freedom. Okay, so degrees of freedom is what? Suppose, uh, take example of the particle which is moving on the bead. Okay, bead which is moving on the rod. Sorry, take example of bead which is moving on the rod in this way. So what is degree of freedom? Degree of freedom means what? Minimum number of independent directions in which that particle is moving without violating any constraints. So I think I will write it down so you will get clear idea about degree of freedom. So degree of freedom is what? Minimum number of independent directions in which particle is moving without violating any constraint imposed on it. Okay, so that particle must be moving without violating constraint. So here this is moving only in along one direction. Okay, so that's why degree of freedom for this is only one. Now if you take example of particle which is moving, okay, on the board. So here there are two independent direction. This word is very important. Independent means linearly independent. So here you have infinite many directions, okay, but all those directions linearly depend only on two directions. That's why this word is there, independent. So here you have degree of freedom of 2. Here you have degree of freedom 1. Similarly, if particle moving three dimensionally, then degree of freedom is 3. Now here if you have only one particle, there is 3 degree of freedom. If you have two particles, okay, you have one. If you have two particles, though, then 1 degree of freedom of this particle and 1 degree of freedom of this particle, so add up to 2. Okay, so similarly if you have n particles, then degree of freedom is n. Here if you have two particles, degree of freedom becomes 4. If you have n particle, degree of freedom becomes 2n. So this is for two dimensional. Now if particle is moving three dimensionally, then you can write degree of freedom as 3n. Okay, so 3 is dimension and n is number of particle. Now constraint, if you have k number of constraint equations, so k is number of constraint equation. Okay, so in that case degree of freedom is reduced to 3n minus k. Okay, so here k is number, only if you have one constraint equation then k is equal to 1. If you have two constraint equation then k is equal to 2. Now these constraint equation must be holonomic. Okay, number of holonomic constraint equation, only holonomic constraint can reduce degree of freedom of that particles. Now we are moving to next point, which is generalized coordinates. So what is mean by generalized coordinate? So generalized coordinate is depend on degree of freedom. Okay, so generalized coordinate is the coordinate which is again minimum coordinate, minimum number of independent directions. Instead of we can read coordinates, so minimum number of coordinates required to specify position of that particle while it is moving. Okay, so such point is known as generalized coordinate. So generalized coordinate is minimum number of coordinates required, okay, to specify position, okay, or state of a particle is known as generalized coordinate. So here if degree of freedom is 3n minus k, then again generalized coordinate is 3n minus k. So we required 3n minus k generalized coordinates to specify position. Now here word arises is the generalized. Why this word arises? Because we know that normal coordinates, what are those coordinates? In Cartesian we have x, y, z. In spherical we have r, theta, phi. In cylindrical we have rho, phi, z. Okay, so these are the real coordinates. Now generalized coordinates is the combination of any of these. You can take one coordinate from Cartesian, one from spherical, one from cylindrical, or even you can specify coordinate which is not in this coordinate system also. So you can choose any coordinate out of any coordinate system or a coordinate which is not in this system. That's why we are calling it as generalized coordinate. But condition is that motion of that system must be does not become complicated. It will become simple equations or simple to solve. So by taking such uh, by such we can say condition into account, generalized coordinate is defined. Now generalized coordinate necessarily need not to have dimensions of length. Okay, it may be angle. Okay, or it may be anything. Again, if you take derivative of generalized coordinate, then that is known as generalized velocities. Again, velocities does not mean to have a unit of velocities. It may be have any other units. Now we are moving to next point, which is configuration space. What is configuration space? So configuration space is the space of generalized coordinates. Space of generalized coordinates. And we know that if n, we can say, is degree of freedom and n number of generalized coordinates are required, then configuration space is n dimensional. If we have 6 degree of freedom and 6 generalized coordinate, okay, then we can say in configuration space is 6 dimensional, not 3 dimensional. Or if you have 9 degrees of freedom, or 9 generalized coordinates are required to specify position, then we can say configuration space is 9 dimensional. Okay, so depending on degrees of freedom, configuration space is defined. Now for simple pendulum is very important system to study, because that represents simple harmonic motion. So for simple pendulum, we know that, suppose this is theta, this is x, this is y axis, and this is x and this is y. Our constraint equation is x square plus y square is equal to L square, z is equal to 0. Now since we have only one simple pendulum, which is having mass m, so how many degrees of freedom and generalized coordinates are there? So 3 are the independent direction, minus here we have two holonomic equation, so 1 degree of freedom is there. Okay, and one generalized coordinate is there for simple pendulum. Now configuration space, for configuration space we need generalized coordinate. So for generalized coordinate is oftenly occur in the constraint equations. So how you can write x position as, suppose this is L, x is equal to L sine theta and y is equal to minus L cos theta. So here you have this theta, so you can choose generalized coordinate which must be present in the equations. So here theta is generalized coordinate. Now if you look into configuration space, then configuration space is one dimensional because only one generalized coordinate is there. Now if you take another example, a particle moving on surface of sphere. Here suppose this is sphere, okay, and particle is moving on the surface. Now you can take x, y, z axis or x, y, z coordinate. Then what are the constraint equation? Okay, r square is equal to constant, or r is equal to constant. So this is only constraint for particle which is moving on surface of sphere. Or you can say x square plus y square plus z square is equal to r square if you choose origin over here. Okay, now if we have only one single particle, so how many degrees of freedom are there? So 3 independent direction minus 1 is only one constraint equation, so we have 2 degree of freedom. So there must be two generalized coordinates. Okay, and in configuration space is must be two dimensional. Now we have to find out what are those generalized coordinates. So for that we need to move into spherical polar coordinate system. So we know that in spherical polar coordinate we require three coordinates to specify position, r, theta and phi. Now r is constant, we have theta and phi. So theta and phi are the two generalized coordinates. Okay, now these are the two angles. Now if you take theta and phi in configuration space, so configuration space becomes two dimensional. So in this way you can choose any dynamical system, which means particle is moving, or we can find out its constraint equation, generalized coordinate, configuration space. Okay, all those factors can be found out. I think with this we stop our lecture over here. In next lecture we will continue our remaining chapter.